Alright, so picking up with lipids. Alright, so this is our second class of biological molecules. Alright, so one of the things about lipids is that they do not form polymers. Alright, so out of three classes, alright, lipids do not form polymers. Alright, so first, before I actually start talking about the different classes of lipids, one of the things you have to become familiar with are your fatty acids. Alright, so your fatty acids. Your fatty acids are basically non-polar. Alright, now, why exactly are they non-polar? Well, this. Because the chemical bonds that hold the atoms together in that fatty acid are covalent bonds, but they're non-polar covalent bonds. And something that's non-polar is also hydrophobic. Alright, so this is what makes your lipids insoluble in water. Alright, so if you look at this fatty acid here, so your isoprene. Alright, so your isoprenoid, alright, consists of a long chain of hydrocarbons. Alright, so hydrocarbons. Alright, so hydrocarbons consist of nothing more than carbon and hydrogen. And that's all you see here is carbon and hydrogen. Alright, so this makes this part of the fatty acid molecule non-polar because carbon-hydrogen bonds are non-polar covalent bonds. Alright, so here, looking at fatty acids, alright, you have two different main types of fatty acids. Alright, you have what we call saturated and what we call unsaturated. Alright, so saturated fatty acids, what that means is that every single carbon atom, alright, has hydrogen atoms attached to it. Alright, so it's completely saturated with hydrogen atoms. And it's a series of single non-polar covalent bonds. Alright. Your unsaturated fatty acid, it has at least one double bond in the fatty acid molecule. Alright, so that means that these carbon atoms here and here are have basically lost or given up hydrogens, and they now have a double bond, a double non-polar covalent bond joining together two carbons. Alright, so non-polar or unsaturated fatty acids have at least one double bond. Now, look at the difference between these two types of fatty acids. Saturated fatty acids are basically long linear chains. Alright, your unsaturated fatty acids are kinked. Alright, they bend. And that's because of this double bond. You have a bend in the molecule. Now, talking about saturated, unsaturated fatty acids. Now, there are some cool key properties about these types of biological molecules. Alright, so your saturated fats. Alright, they consist of long linear chains of fatty acids. Now, the fact that they're long linear chains allows them to stick closer together with other saturated fats. Alright, so the fact that they can stick closer together means that at room temperature, alright, they're solids. Those fatty acid molecules are closer together. Alright, now your unsaturated fats, alright, notice here that the individual fatty acids are not as closely compacted with one another. And that's because of the double bonds within the backbone of the fatty acid. Alright, so that allows for there to be bends. Alright, and these bends, these kinks, alright, increase the amount of space between your fatty acid molecules. Alright, so the increased space between your fatty acid molecules allows for these types of fats to be liquid at room temperature. Alright, so things like oils. Now, you can have other substances like your beeswax, for instance. It's a saturated fatty acid, but the hydrocarbon tails are really, really long. Alright, so it's also a kind of a solid at room temperature. Now, so one of the big topics nowadays has to do with trans fats. So, what exactly are trans fats? Alright, well, here you're talking about basically this process of what we call hydrogenation. Alright, so hydrogenation. Alright, so basically what you're doing is you're basically adding hydrogens. Alright, you're hydrogenating it. Alright, so you take your, in this case here, your unsaturated fat here. Alright, you get that nice double bond. And what you do is you try to, you'll have companies that will basically add hydrogens to it. They will partially hydrogenate it. So you go from basically this cis configuration here to having a trans configuration. Alright, now this trans configuration is actually quite beneficial. Alright, because you basically take a substance that is going to have a much longer shelf life. Alright, and a product that has a much longer shelf life is good for business. You can sell more product. Now you can completely hydrogenate, go from this unsaturated fatty acid to saturated fat, which is also unhealthy for our diets. But usually you'll see companies partially hydrogenate. Now, you notice that a lot of food companies and restaurants are actually phasing out trans fats. Right, that's a big thing nowadays. Now notice that a company can actually modify, regulate how much trans fats they actually have in their foods, and they also can regulate their food product label. So basically, the food companies, they can actually have basically 0.5 grams of trans fat in a product, and basically they'll kind of say there's basically no trans fats per serving. Alright, they're allowed that kind of flexibility. So even though it says 0 grams of trans fat, you can't trust it because it's based on the serving size. Alright, and they can play around with their serving size as much as they want. So what you have to do is you actually have to look in the ingredients of a food product and look for anything that says hydrogenated or partially hydrogenated vegetable oil or something along those lines. And I'll tell you that it has trans fats in it. You know, even though it says 0 trans fats, if you read the ingredient list, you'll notice that there are trans fats in the product. Alright, so trans fats increase the shelf life, preserve it. They add a little bit of flavor, but they're really not good for you. So looking at trans fats, so here, basically, you're looking at going from something that's a vegetable oil, completely unsaturated, to something that is highly saturated, like shortening. And so you'll end up with products like soft margarine and stick margarine that are basically your semi-solids. Alright? These are your partially hydrogenated products. A lot of your frozen foods you can purchase at the supermarket have trans fats in them. Anything that's like pre-made, pre-mixed, trans fats. Alright, so what exactly is wrong with trans fats? Well, it has to do with this idea that fat's becoming more and more solid. Alright, and we're already having issues with saturated fats in our diet. Alright, trans fats are this like hybrid in between, and so they're just as bad for our diet, if not worse. And so what they actually lead to is the formation of these plaques in our arteries. And it all has to do with the levels of cholesterol. So basically, ingestion of trans fats and saturated fats, or you have a higher level of these bad fats in our diet, so these LDLs, or low density lipoproteins, and you build up this levels of cholesterol in the artery walls and plaque formation, which leads to decreased blood flow and hardening of the arteries and increases your chances of having a stroke or a heart attack, as opposed to your high density lipoproteins. Alright, so the first type of lipid we're going to talk about are your fats.
Butter, lard, margarine, and salad oil are composed of lipids called fats. To make a fat molecule, 3 fatty acids bind to a molecule of glycerol. For this reason, fat molecules are technically called triglycerides. Fat molecules do not mix with water because they have 3 long nonpolar hydrocarbon tails. Cells use fats for energy storage because the tails hold more potential energy than other biological molecules. The fatty acid tails in a fat can vary in length. A very important characteristic of fats is the number of double bonds in the hydrocarbon tails. Fats that contain only single bonds are called saturated fats. Fats containing double bonds in 1 or more tails are called unsaturated fats. Unsaturated fats tend to be liquid at room temperature. Vegetable oils are examples. Saturated fats, like butter and lard, are solid at room temperature. Saturated fats in the diet can lead to heart disease, while unsaturated fats are safer.
Alright, so looking at fats. Alright, so fats consist of 2 components. You have glycerol, and which is basically a sugar alcohol, and then you have fatty acid tails. Alright, so basically you have 1 glycerol molecule and 3 fatty acid tails make up 1 molecule of fat. Now, again, to reiterate the synthesis of biological molecules. Alright, so here, alright, notice you have in your glycerol molecule, you have a hydrogen atom attached to this hydroxyl group. Here, in your fatty acid, you have at the very end, you have your carboxyl group with this free OH. Alright, well, if you remove a hydrogen and remove this OH group, you basically remove a molecule of water. Alright, so your fatty acids are attached to the backbone of this glycerol molecule through a dehydration reaction. Alright, so the type of covalent bond that joins your fatty acid tail to your glycerol backbone is referred to as a ester linkage. Alright, so again, you're going to want to keep in mind the type of covalent bond that joins and links your fatty acid molecule to your glycerol backbone. Alright, so your fatty acids, or your fats. Your fats can have fatty acid tails that vary in length. Alright, they can have fatty acids that are either all saturated or all unsaturated, or you could end up with a variety. You could have two fatty acid tails that are saturated and one unsaturated. You can end up with two that are unsaturated and one saturated. Alright, it can vary. Alright, so you have different types of fat molecules based on that, the length of the chain and whether they're saturated or unsaturated fatty acids, which is going to influence the behavior of the fat. Now, when we talk about fats, alright, they're mainly used as a good source of energy. Now, we've talked about this. We talked about the fact that your fats, since they're nothing more than these long chains of hydrocarbons, that they have all this potential energy stored in these nonpolar covalent bonds. And that there's actually more energy stored in a molecule of fat than in a carbohydrate, a simple sugar. Alright. One of the other functions of fat is going to be, besides energy storage, alright, you're also talking about insulation of organs. Alright, so maintaining body heat, insulating the organs, the core of the body. And then you also have cushioning for organs. Alright, so it's a nice buffer. Alright, so the next class of lipids is going to be your phospholipids. Now, your phospholipids are totally different from your fats. Alright, so your fats are insoluble in water. Alright, your phospholipids, alright, think about this. Phospholipids. Phosphate group. Alright, so here you have a functional group, a phosphate. Now you have this phosphate group that's attached to your glycerol backbone. Alright, so here's your little phosphate group right here. And we talked about phosphate. Alright, we talked about how phosphate is a polar functional group. Alright, so here you have this polar functional group up top. This phosphate group. And then here you have two fatty acid tails, which are non-polar. So you have a molecule that's both polar and non-polar, right, in different regions. All right, what we call this is amphipathic. All right, so the molecule is both polar and non-polar. So what happens is you can basically take these phospholipids and toss it into water, and your phospholipids will actually aggregate, and it'll form this bilayer. Alright, so here you have a simple cartoon image of a phospholipid. So you have your hydrophilic head. Alright, so since this is polar, it's soluble in water. Your nonpolar portion is insoluble. Alright, so your fatty acid tails are represented by this. Alright, so notice that if you look at your bilayer, alright, so your phospholipid bilayer is basically what makes up the cell. Alright, it defines the outer boundary of the cell. Alright, a cell is not a cell without its cell membrane. So, what you have here is you have your polar head groups sticking outside. Alright, so the aqueous environment outside. And then you have inside the cell, here. Aqueous environment inside the cell. And here you have your fatty acid tails that are in the middle. Alright, so they try to get as far away from water as they can. Alright, so your polar head groups interact with water. Alright, your non-polar fatty acids shy away from the water and are in the middle of the bilayer. Alright, so if you toss phospholipids into water, they'll form what we call micelles. Basically, they'll form little vesicles. Alright, your polar head group interacts with water because it's polar, and your fatty acid tails are nonpolar. Alright, so they try to get away from water as best they can. So that's why they go to the interior. Now, the next group of lipids are going to be your steroids. Alright, so your steroids consist of 4 fused rings. So, you actually end up with this part of the molecule being non-polar. Alright? Because it's nothing more than a series of hydrocarbons. Alright, but here you end up with basically this OH group and the rest of this fused 4-carbon ring, which makes this part of the molecule polar. Alright, so cholesterol is basically this molecule here. Alright, so cholesterol is important in terms of animal cell membranes, or you don't find it in plant cell membranes, you find it in animal cell membranes. Now, when we talk about animal and plant cell structure, we'll come back to cholesterol and the role it plays in the membrane. Alright, but right now just know that cholesterol is a component of cell membrane of animal cells. Alright, now steroids. Alright, they're important components of the cell membrane. They're vitamins, and they're also hormones. Alright, so chemical messengers. Alright, so this kind of gives you a space-filling model of cholesterol. And here you kind of have a stick model of the cholesterol. So basically you have your long fatty acid tail there, your hydrocarbon tail, and up here you have your OH group. And then here you have your nice little 4-ring fused structure of the cholesterol, of your steroid molecule.